Today we're going to do code objects, function objects, and closures. So the objective of today is to understand how functions in Python, which we've covered briefly, the concept of functions, how they're just simply Py objects. They're just another kind of object, and we're going to look at how that works in detail. So remember last time we actually covered example data types. So example data types such as strings, and in your assignment we're going to do ints and tuples. But basically every type of data in Python is some kind of an object. And the big new thing today is just to show how functions are just objects as well, just like any other kind. It just so happens that you can call functions as functions are a type of object that you can call with the parentheses operator, but otherwise they're just like any other object. So today the main event is code objects, and then function objects, and this concept called closures.
You lost your projector.
Oh, did I lose the projector? Wow, that's weird. I think here we're good. Okay, nice. This thing is just not on tight. Okay, so just to begin, make sure this thing's recording. Just to begin, we'll go to our. I guess we can go to our console. Let me make it a little larger. So let's just go into just Python itself. Just type Python, just go into it, the interpreter, and then we're just going to define a function. Def foo, and then that takes x and y as parameters, colon, and then indent, and then, I don't know, z equals x plus y. You have to indent again. Return z, and you have to press enter twice. So now you actually should have a function defined when so I think everyone who wants to follow along can just do that. So if you type in foo, the type of this, it's a function. It's some kind of a function object in Python. So running this def foo line will actually define a function in Python. So if I say bar equals foo, so what happens there if I execute this line? Well, nothing will print out, but what is bar now? It's a function. It's the same thing as foo. Right. Bar and foo actually, they're the same memory address. They just point to the same thing. I mean, bar and foo are just names for a function. So we actually run it in this Python tutor tool. We go to pythontutor.com and we run this code. Well, we have to get rid of these spaces. So we're going to run this. If we do that, we step through the first line. Notice how at the beginning of execution there is no, there's nothing on the screen. There's no variables defined right now, right? We haven't executed any lines yet. And when we step through and execute def foo, when we execute this def line, we actually define a global variable foo that points to some function object foo. I mean, this function object has a name foo, but it's confusing because the global variable is also named foo. But conceptually, this is some object somewhere in Python, and this is just a name in the global namespace, and it points to it. And then when I execute bar, when I execute the next line, what should happen in this diagram? Should I have two copies of foo on the side? Just one, right? Yep, so they point to the same thing. All right, so I want to make sure this is clear that that bar and foo are simply two names that are alias to the same object. There's only one function object that was created. This function object was created when we executed this line. So notice the function object wasn't created at the beginning of time. Like, there's nothing here. When you go like this, it gets created. Only when you execute does it get created. So, for example, if I try to do it the other way, if I try to do bar equals foo here, then what do you think happens when I execute this line? Yeah, it's not defined. Right. It's just, this is error, not defined. Because even though you're, like, if you're in a language like Java or C++, there is actually a function named foo, but in Python, this foo doesn't exist unless you actually execute the line. Everything happens when things are running to keep things simple. So if you say bar equals foo up here, it just breaks because we don't know what foo is yet. Okay, so we have that. So now that, let me just get our picture back. Oops. To normal. Okay, so foo and bar both point to this thing that's a function object. So let's look inside the function object in Python and see what properties it has. So we're going to go back to our interpreter. Oops. We're going back to our interpreter, and now foo, if you type foo, it's a function. Remember dir on anything in Python? In the Python interpreter, it gives you what's inside. So these are all the things that are inside this function object that we can look at. There are some things like func name, which is probably the name of the function. So if we say foo dot func name, it's foo. It's just saved when you define the function. There's foo dot func dict. This actually doesn't have anything. This is for more complicated cases here. This is for probably default arguments. Foo dot func globals. This is interesting. So what do you think this func globals is? What does all this look like? And ideas? So this is what's in the global scope when you define foo. So if you, well, it's hard to see here, but if you see when you define foo here, the global frame that foo points to has objects like foo and bar in it. So if you actually squint really hard, there's a bar that goes to function. There should also be a foo. Oh, my printing is kind of big. There should also be a foo that goes to. Oops. There's a foo thing here, the dictionary that maps to a function, and there's also bar that maps to a function. There's a built-ins thing that maps to a bunch of built-in things in Python and other stuff. So this is basically func globals is just a pointer to the global dictionary, so that when you want to access global variables, say in your functions code, you can know which global variables to access. So then the question is, why do you think you need to have func globals? Because isn't there just one globals? Like, I mean, there's just one global scope. So why does every function need to point to its own globals?
Because when you modify one function, then all the pointers point to that would also change.
Okay, when you modify the function or modify which thing?
Global object. Yeah.
The which kind of object?
It's a global object.
So objects that are global. Okay, so right. So if you have, there's a global thing right here, right, which has a bunch of mappings, and then we're saying that foo dot func globals points to this thing, and then bar dot func globals also points to this thing. So right, so if in your idea, if you modify something like globals, they both see it, right? Both of them see it. But my question was, why do you even need to have a pointer global? Why don't you just have a universal pointer that everyone just uses for global? Because there's just only one global table. There's only still one global table. So why does everybody need to point to the same globals? Why don't you just have this as a global variable, I guess?
You want to do like nested functions?
Okay, nested functions, good. So one thing, we'll get to this later in the class. If you want to do nested functions, maybe this global is different than that global. So that's sort of the answer. I think the answer is that the global is really in the eye of the beholder, right? So every file has its own globals, right? So if in this very simple example here, these only have one file, right? There's only one file here. Everything's in one file. But imagine if you had Python code that lives in multiple files. If you had, so later, oops. If you had code that, that's actually a lighter color. If you had code that that lived in multiple files, then your global might not be the same as my global, right? So really the global is the global for your file. So if you have a Python project that has 10 different files, each one of them actually has a different global, because the global for one person is not, for one function, is not the same as the global for another one. So it's similar to the nested function idea, but also a little different. So everybody needs to keep track of their own globals. So dir foo, what's in foo again? So the other important thing in foo is this func code. So what is func underscore code? So what kind of type is it, first of all? It's a code object, right? So it's a pointer to the actual code. So interestingly, when you think of a function, you think of a function containing its code, right? You actually think of a function as, this function is a block of code somewhere. So, in this visualization I made, it's pretty simple. I just put everything in there. But really, the function is just a shell. The function actually doesn't have any code in it. It actually has a pointer to a separate object of code. So, so the example is, there's actually foo is actually some kind of a function object, and then the function object inside has a func code field, and that's actually a code object. So what do you think is in the code object itself? Yeah, the bytecode, right. So the code object has the bytecode. So the function doesn't actually have any bytecode. The code object has a bytecode. So in addition to the code, a function has a func globals and then some other stuff. So this thing points to the globals dictionary, right? To whatever the globals is. So a function really, if you think about it, has there's a bunch of other stuff. It actually has two things. Conceptually, it has a pointer to what code it contains, and also has a pointer to its environment, to where it is defined. So if I imagine, I don't know how we would actually get this to work, but if I have two files, I have, a.py and another file, b.py, and I have some global here, x equals 10. Here I have x equals 20, and then I have def foo, some code. And then here I have def foo, some code. Imagine this code is exactly identical. So if this code is exactly identical, Python could presumably, I don't think it actually does, but if this bytecode is exactly the same, the exact same sequence, we could presumably have just one code object that represents both bytecodes, because it's the same thing. Now this foo, this foo will point to a function object that points to this code. Drawing's gonna get a little messy. This foo will point to a function object that points to the same code, let's say, right? I think in reality it'll point to two different pieces of code that are exactly identical, but let's say if one of you for your project wants to optimize this is a good way to optimize. So it's exact same code, just have the same code object. But the difference between these two functions is that this function's global points up to here, and this function's global points up to there, right? So even though we have the exact same code, so actually let's say the code says print x. I'm just saying, okay? Let's just say this code is print x. So the code itself is some bytecode for print x, right? Whatever print x is, load constant, load global, print whatever, right? With the exact same code, if I execute it here, it'll print out 20. If I execute it here, it'll print out 10, right? So the exact same code can do different things when you run it. And the only difference is that the global pointer for these two functions point to different globals. So at runtime, when you execute this code and you load the variable, you either load 20 if you're here, or you load 10 if you're here. That make sense? So the bytecode itself doesn't tell you what is going to go on when you run it. Just like from assignment 1, when I gave you a piece of bytecode with like x and y, we had no idea what that's going to print out when you run it. We just know what you're supposed to do with x and y. And the way you look up x and y is from these globals or from other stuff. So this is the distinction between a function object and a code object. Make sense? So if anyone asks you, what's the difference between a function and code object? The code object has the bytecode itself, the instructions, and the function object points to a code object, but also has some environment, some notion of what variables it has access to. Yeah, so it's called a closure. Yeah, so that's one thing you can call it. Okay, questions at this point about function and code objects? So let me just go inside of func code. So func code is a code object, and it has a bunch of fields. Remember, this is from the very first class. We looked at bytecodes. So func code dot, co underscore code. This is the actual bytecode, right? So the code object has a bunch of fields inside. This is the actual bytecode, and it's in some weird format. And if we look all these up and we translate them, it has a bunch of instructions and arguments and so forth. It looks kind of weird because it's all compressed. But so CO code is the actual bytecode. There's other stuff like CO names, CO file name, constants, flags, other stuff. So basically the code itself contains local, not only the bytecode, but also some information like what are the constants in the code, what are some of the other stuff. But so the code object is created. So here's a kind of subtle issue, that the function object isn't created until you actually run that, execute that line of code. But all these code objects have actually been pre-compiled. So when you compile Python before you even run it, all the code objects are already there in memory. It's just up to the function objects to point to it. So when you compile this file, there's actually a code object with this bytecode already. And when you create this function foo, it would just simply point to this existing code object. So the code object is made during the compilation stage, and we had to skip over that in this class. Okay, so now we have functions, we have code. So when you actually execute a frame, we did the right. So when we did the function execution of the frame with the with executing functions in the interpreter, remember in C eval, what we did is we got the function and then we grabbed the code out of it, and then we actually started executing that bytecode. So that's just a way of executing code. So with that, we can actually start diving into the C code. So that was a high-level overview of what functions and code objects are. So if we go to include, capital I again, remember these are all the header files. So let's just start with code.h. So Python 278/include/code.h. So if we look at that, this is basically the definition, a PyCode object. So this is a PyCode object, which is a subclass of object, again, or PyObject. It's just, they're all Py objects. Notice how these things are familiar. They're actually exposed by the Python. So how many arguments, how many local variables, stack size. This is an object that represents the code. I think this is just a string. I'm pretty sure it's just a string. A list of constants, a list of names in the code, and a list of other stuff. And this is more debugging information, a file name and the name. But essentially the code is here, right? It's all this information. And the information is actually exposed by... this information is actually exposed... what do we do? Oops. Foo xy. Turn C. Notice you can actually access these from Python. So let's do co-code. That's a bunch of stuff. Co names. Oops. Name. There's nothing in name. Co arg count. Two. So there's two arguments, right? So there's two arguments to this code, x and y. There's two arguments. So it's just information about it, right? So basically it's information about this piece of code. What the code object does not contain, as you notice here, is it doesn't contain any pointers to the global variable. So by itself, the code can't execute. It needs to have some notion of what global variables and other variables it can access. It can access local variables, I guess, all at once. Yeah.
How come when you access the co names, there is empty?
Yeah, it's empty. I think it's because they actually use a macro. So actually, sorry, not macro. So we're going to do import dis to disassemble. So dis.dis foo. This disassembles foo. This bytecode uses a load fast opcode, which is a fast way of loading local variables. So it actually doesn't need to be named. These variables don't actually need to be named. But then you have a good point of why do they actually have names on here? Let's actually dig in to see it. Because it needs to know it's X, Y, Z somewhere, yeah. Right? So let's actually fine worded. CO free bars? No, it's CO. var names. Sorry, var names is the names. Sorry. These are the names.
Oh, wow.
Yeah. So var names is that actually in here? Yeah, var names is local variable names is a tuple of strings. So notice how you access this in Python, but it's actually C code. It's running. So var names is actually the local variable names is a tuple. This is strings names used. I think this might be used when there's too many or something. I don't actually know for sure. Var names is the var name. These are free variable, cell variable. These have to do with nested functions. But yeah, I guess var names is the thing. Because remember that the opcode here is a load fast. So it actually just loads it really fast. It just says, give me the 0th local variable, give me the first local variable. It doesn't actually look up a dictionary. It's just an array access. But we need to actually map it to names, so X and Y. So var names is purely for debugging. Yep.
The recall from the first assignment. Okay. I can ask you offline.
Okay, or we can look at the interpreter loop later, yeah. Okay, so that's a code object. It's decently straightforward. There's a bunch of flags for like different options and stuff you don't have to worry about. There's just more weird things. Pi code check. This checks to see if it's actually a code object or something else. Pi code. Add to line, address pair, optimize. Okay, so let's jump to, get out of this file, jump to objects, capital O. Recall objects has every kind of object in the standard built-in. So code object.c in capital O objects. So we're going to go into that. Okay, so when you go into that, basically this, there's a lot of things here, but PyCode new is the constructor for the code object. So again, C doesn't have object-oriented programming, but they're faking it by just, basically, in order to, if you want to create a new PyCode object, this will create a new PyCode object, you pass in all the parameters you need. How many arguments, how many locals, the bytecode itself, the variable names, everything. You basically pass in everything, it does some sanity checks, and then it allocates and creates a new code object for you. So where Py object new, I guess this is the generic constructor for constructing objects, and it does a bunch of increment reference counting, and then it returns a new object. So this does what you expect it to do, it just, as a constructor, creates a new code object on the fly. So the compiler actually creates a bunch of code objects. There's a bunch of utility functions for code. Code new, we don't need to worry about this. Deallocate, so this kind of frees up the code object when you're done with it, so it decrements the reference counts and then deletes the object. Code repr, compare. So this compares two code objects to see whether they're equal. And it's very straightforward, it's just what you think. It actually compares all the fields. Is this field the same as this field? Is this field the same as this field? Standard object-oriented stuff. Rich compare, I guess this does less than or greater than. I don't know why you want less than or greater than for code. Hash is a way of creating a unique identifier for the code. So just like any kind of object, what hash does is it calls hash on all of its constituent parts, and then it mushes them together using some operator. This uses exclusive OR, right? Is this XOR in C? Yeah. So it uses something to just mush together all the numbers into some number. So this is just the hash function they chose. So this is the type identifier. So remember how, this is actually pretty important. So there's a type object. So remember how every object in Python has a type, right? Every object has a pointer to its type. This happens to be the code type. And the type object has a bunch of methods that the generic object will call, right? So if you say add or equals or whatever, it'll actually find the right method in here and just call us. So if you try to call compare on two code objects, it will call this code compare because it knows one of the things it codes, it actually jumps in here. So every object has a type identifier. It's called PyCode type. So you don't have to jump to this now, but if you go to string object.c, PyString type should be right here. So this is a PyString type. And again, it contains slots for all the functions that you can possibly call on strings, such as compare. So if you do do they have compare? No, they don't compare. They use a rich compare, which is, I guess, a better sort of compare. If you do a comparison on two strings, the object, the bytecode interpreter will say, I want to compare two things. I don't know what they are. And then it goes into some crazy code like we mentioned last time, and then it looks for its type. And then if it's it actually just calls the rich compare method for something, and it just happens that if the object is a string, it will call the string code compare. If it happens that the object is a code, it just calls the code rich compare function. All this is determined at runtime. The compiler knows nothing about it. Yes?
Does the dir command in the interpreter just looks at this thing and then?
The dir command actually, that's a good question. I think it exposes some interface. So the dir command, let's see what the dir command does. Because this is C land, right? This is all C.
Mm-hmm.
So the dir command is all in Python. So the Python objects do expose, the C objects expose some sort of interface that the Python objects can access. I can't find it right here. But there's some kind of way to bridge the two. But yeah.
So this is like more detailed.
Yeah, there's more detail. Yeah, this is the C version. Yeah, so I mean, the dir method, all that, it actually just grabs those. It actually looks at the attributes directly. But it doesn't have all of them, right? It doesn't expose all of them. So somebody had to write a piece of code that says map this to this, this to this, this name to this. But we won't look in the Python interface. Okay, so we have a function. We have a code object now. So the code object is decently straightforward. You can't do that much if you just create a new code object. And usually you create a new code object. The compiler creates a new code object for you. So the process of compiling Python is it actually when you're compiling Python, the compiler just creates these. You have a source code file. Pen broke again. You have a source code file, and you when you hit compile, well, I guess when you run Python, it first compiles the source code into bytecode. That step will create all the code objects because bytecodes are code objects, right? So as soon as you compile your Python code before you even run it, all the code objects will exist already. Now, the function objects don't exist until you actually run the line of code defining the function. But all the code objects are there waiting for you because it's all just bytecode. So, so when you compile Python code, you have a py file. When you compile it, every function gets its own code object. And then we're just waiting for those code objects to be assigned to the function objects when you're running stuff. So it's sort of this weird thing. Actually, we can show you. So let's actually define a function. I don't even remember which example we did. Okay, God, this actually has two things inside. So if I import test, import foo, import disassemble foo. So this disassembles the foo object. Disassembles the code, and this code is all just bytecode, right? This is what we saw from like the first class and all the classes. Okay, so let's actually go into the function object because we already did the code object. So Python, let's do include capital I again, and now let's do function or func object.h, func. Okay, so this comment says basically what we've been going over in class so far. So you can just take a minute to read this. Take a minute to read this. I fix my pen. It's syncing stuff.
Includes function dot.
Yeah, include capital I include. I'll look at my notes from my phone here. The example we use is foo bar.
Should not be confused. Okay.
Yeah, so read that. I'm gonna load up another piece of code while you read this. Oops. So we're gonna call this test.py, def_foo_x, def_y. Don't worry about what I'm writing right now. I'm just queuing it up for the next thing. Okay, so here we'll get done reading that. Basically, it's what I was just going over, that functions and code objects are not the same thing. Function objects are created when you execute the def statement. When you define a function, they reference a code object, which has nothing more than just syntactic. So function object, what is it? Again, there's a py object head. It's just a py object. There's a func code, which we've seen. There's the globals. There are some defaults. Defaults are like when you pass in default parameters. There's a closure, which we'll go over later on in this hour. There's some documentation. So Python, you can write documentation in the function body itself or the header itself. It's just convenient. Name is the name of the function. There's some other stuff. But closure. Okay, let's not worry about the closure yet. So right now we just have to know function has code. So anything else? These are all helper functions you can call on it. You can create a new function, get the code out of the function, get the global out of the function, get a bunch of stuff out of the function. They're just things to help you deal with functions. So if we go now to objects, capital O, and then funcobject.c. And wait for it to load, and this is all the stuff for functions. So it's what you would expect. PyFunction new is we're actually going to create a new function. And notice the signature here. We're actually taking in a code, we're taking in a code object, and we're taking in a globals pointer to globals. So you create a function by putting in code and putting in what globals you want. And then this does a bunch of stuff. You can get the code out of the function, not surprising. Get the globals out of the function. Let's see, a bunch of other stuff. Closures. This is the answer to your thing. This is what allows Python to access these things. It's called a PyMemberDef thing. So what this allows you to do is this actually maps the Python name of, say, func closure to actually grabbing a func closure field from your C code. So this is some other mechanism behind the scenes. We won't look into this, but this basically allows you to access directly your variables in C in the Python itself. So if you declare your own classes, you can do this. But I wouldn't worry about this part. Get dictionary. These are all just helpers, just to help you manipulate the function, getting the globals, getting the code out. More. Here we go, funcdict, funcname. So I guess this member allows you to read and write to it. Actually, yeah, because the one before, I'm just going to go back because you had a question on it. These are read-only. I think these are read-only. Or write restricted or whatever. So you can actually write to them in Pythons. Maybe you can. Let's see. I don't have another thing up. So if I do def-foo xy, I should just really keep one of this open. So typing in every time. That's the name. Let's try to set it. Oh, you can set it. Okay. Weird. Okay. Well, that's just for debugging, right? It's just call bar blah, blah, blah. It's just to debug. It's just to help you debug, to identify it. It doesn't really matter. So I guess you can set it. But these ones you can actually set. So these func. Oh, name is settable. So name you can't set, and so is code.
Yeah, it looks like you can't screw with like the globals and whatnot.
Yeah, so the globals you can't screw. Let's see.
Which would make sense.
Func clips. Okay, good. Read-only attribute. Okay. So globals you can't just set to something else. Okay. So basically this says that, I guess, if you try to access func name, you can get it with get name, or you can set it with set name. So it's just like if you try to set the name, we call the set name function. So it kind of maps from the Python to the C functions. So, and then there's some strings for helping. Okay, so nothing super interesting here. Blah, 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 blah. And again, this is the function type thing for doing stuff. And the most important part of this function type is the call method, because the call is what you can use to call functions. So this function call actually calls the function and does stuff with it. So it does a bunch of things: get code, get closure, eval, code, eval. Yeah. So remember, this is the interpreter loop, right? So this is the when you make a function call, you conceptually unpack all the arguments, get all. This is a lot of cruft. This is the big centerpiece right here. that we call pyeval codec. But this is the main interpreter function, right? I think this is it. They call a lot of things, so I'm gonna. You don't need to jump to this one yet, but yeah, this is the main. Is that the main one, or is this?
No, it's different.
Yeah, it's another one. Well, eval frame is the right one, right? Yeah, no, eval frame X is the right one. Yeah, that's the big one. But anyways, all of these call eventually evaluate the frame.
Okay.
Like this evaluates a piece of code. I guess it gets the code out, it gets the globals out, it gets a bunch of other things out, just a bunch of extra information. It just kind of says
Probably
go.
makes the frame, right?
Yeah, makes a frame. That's true. Yeah, I think this actually makes a frame because there's no frame object yet. So actually, let's out of curiosity, let's go to here. Yep, frame object.
Yeah.
F is it? Yep, frame new right here. You're right. See, and it creates a frame object out of the code and the globals and the locals. So frame, as you recall from like the second lecture, is the runtime representation of a function running. So function code, frames, all similar but different. Okay, so moving on, there's not much else here for functions. Okay, so by now we should be able to get how functions and code objects work. So recall foo is a function. You can actually call it, right? Foo123. Foo has a func code inside, which has var names XYZ. It has code, which is the bytecode, and so on. Okay, so by now you should be able to, any function you write in Python, you can kind of see how there's no magic. It's just a bunch of code, and then it has a pointer to it, and it all executes. So actually, let's go through the call function. That's a good exercise. So we're going to go a little bit fast, but you don't need to do this on your assignment. So I just want to, out of curiosity, let's actually call a function. So the call function bytecode is here. Okay, call function is a bytecode. So imagine I execute call function as a bytecode. This will go to call function, which is the underscore lowercase call function. Here's call function. There's a bunch of arguments. It like finds the arguments. It does something. Fails here. It's a method now. If it's a function, fast function. Okay, so if it's a function, call this fast function. We're just going to jump in fast function. It gets the code out, right? Gets the CO, the code object out of the function, gets globals, gets defaults, and does a bunch of checks. There's a frame. It actually creates a new frame right here. Sets the locals, globals, does all this fun stuff, and then bam, eval frame X. That's our giant. Giant main interpreter loop. I think that's it, right? Yeah, that's when you annotate it, right? I always get the names confused because there's so many names. But yeah, so essentially what we just did was I was jumping around a lot. We set up the frame. From the function object, right? We have a function object. We rip out the code from the function object. We rip out the globals from the function object and some other defaults. And then we pass all this in to make a new frame. And then we push the local variables on. We went over this in an earlier class, right? We push all things on, and then we just call this magic function with our frame, which knows our code and our globals and stuff, and then that will go and call the main interpreter loop. And this main interpreter loop is recursive, right? Because imagine we are already in pyeval eval frame X. Then when we call a function, we call pyeval frame X again, and then we'll call again and again. And every level is like a layer in our stack. Cool. Okay, so the last concept of the day is this thing called closures. So how many of you have seen code that looks roughly like, I need to open up that looks roughly like this with a nesting inside. Okay, so so can you explain what this thing does? Or just very high level. I mean, not every step, but just conceptually, what does it mean for the bar to be inside the foo?
Basically,
Uh-huh. Right. Right. So you can define a function inside of another function. In Python, indentation is used to denote scope. So you can actually, normally the way you would write bar is you would define it, you just define it outside, right, like a regular bar. But you can also define it inside of another function. So the way this works is that when you define another function inside another function, this x, you notice how this x will actually look in the enclosing scope, which is this x right here. So notice there's no x on global. Actually, let's do a global x. Global x equals 1,000. There's a global x. There's an x in the local variable foo. So when I'm in bar and I say what's my x, it's actually the x that we pass in foo, not the global x. And it's called a closure because we're enclosing the scope of bar in the scope of foo itself. So I'm actually going to show you with a picture. I'm actually going to run it through the Python tutor to see a diagram. But so we'll do the Python intuition first, and then we'll do the we'll do it through the interpreter. Okay, so I'm going to reload this. I'm going to paste this code in. Okay, so we're going to visualize. Only 12 steps, so not too many steps. Okay, step 1, we're going to define x as 1,000. This should not surprise anybody. Global has x 1,000, right? So after we step through the step, there's only one thing in our global frame. It's 1,000. It's an integer. The next step, what should happen when I step over the next step? What's the picture going to be like? A function object. Yeah. Yep. So foo points to function object. So notice when I step through, there's no bar anywhere. And there's no bar because we haven't executed foo yet. Bar doesn't exist because we didn't even run the code inside of foo. Bar only exists when we go and run foo. All right. So foo points to a foo object. That's a function. Now, I kind of cheated when I said this because behind the scenes, there's actually bytecode for bar and bytecode for foo already precompiled somewhere. It's just stashed behind the scenes. They're just kind of stashed behind the scenes because the compiler actually makes the bytecode, but we can't see them yet. We can't get to them. They're just hiding somewhere, waiting for us to find it. Okay, so when I execute this line, what will happen is b1 equals foo of 10. We're actually going to call foo with 10 as the parameter. So when I hit enter, I enter foo. This is the frame of foo. And x is now 10 because I passed in 10 to foo here. Does that make sense? X is now 10. When I execute the next line, what happens if I execute this next line?
Bar.
Okay, so what will appear?
New object bar.
New object bar, and it points to what?
Actually, it's a function, new function.
New function bar. So where is that bar going to appear? Here or here?
Down.
In the foo, right? Because we define the function bar within foo. So this, you're absolutely right. So we step, we get that, all right? If we step, we get this. We get bar is now a function that points to this bar. Now the Python tutor doesn't have for compactness, it just represents these parent pointers as a label f1. What this is essentially saying is that this bar function has a parent pointing to this frame. It means that it was actually defined within the scope of this frame. So this is called a closure, that bar itself has some code, but also has a pointer to whoever defined me. This who defined me. And this will become important later on, because now when I return bar, so return just sets the return value to bar, and we're going to assign bar the return value to b1. Remember how b1 equals foo10. I go here. It's jiggled around a little bit, but it's okay. Okay, so what's going on here? This foo function has exited, so it's kind of grayed out. There's nothing here anymore, but we can't throw it away because bar needs it, because bar's f1 actually points to it. You see that? So we can't actually throw away this frame. We can't garbage collect it. We kind of have to conceptually keep it around. The Python interpreter doesn't actually do that. It optimizes a little bit, but conceptually speaking, this is what it's doing. It's keeping this frame or part of this frame around.
What do we need? We already have the return value.
Yeah, we have the return value, but let's when we call bar, we need to get this x. We need to get this x out of it.
But hasn't that been called? Like you already. Okay.
We never saved the x in bar, right?
No, right now.
So the way that the x is saved is actually it's referencing this original frame.
But why do we care about x here?
Why do you care about x? Because we're gonna actually call bar because bar uses x. Bar will use x. So if we don't keep that around, we're gonna mistakenly use the global x, which we don't want to do. Does that make sense? Okay, so we keep this around, and now let's do a b2. So now this is why it. Oh, sorry. Let's actually. So I'm gonna make my example a little bit more complicated, but don't worry about it. So let's try to. We're just gonna call b1. b1 on what's your favorite number? 1. b2 on 1.
But you have called B1.
So let's step through again. Okay, we're here. Okay, remember the closures? Now b1, what is b1? b1 is just a function. We can call it, right? b1 is just a function. We can call it however we like. What are we going to call it on? We're going to call it on 1. So when we call it, the 1 gets passed into this y, right? So let's call it. Now we jump in here. Now y is 1, not surprising, right? Now this frame has a parent f1 again. And then because this thing came from f1. Now here's the crucial part. The crucial part is we're going to step. Now what does that parent x plus y do now? So what is it going to look up? 11, right? So the y we get from here, it's just a local. And the x, this is the key part of why the closure matters. It's going to crawl up this thing and find the x here first. If it doesn't find an x here, it'll crawl up and find it in the globals, but it will find it in the x here first. And that's why there's a nested. That's why I have to keep this frame around. So it has to find x is 10.
Yeah.
So now this will actually print out 11, right? So if I step, there's a console on the bottom, 11. Okay, that's surprising. Okay, now here's where more closures come in. So we're gonna get out. Great, we're done with b1. Now we're gonna do the same thing, except we're gonna do b2, call foo of 20. So now in this frame of foo, x is 20 now, right? So now when I return bar, here, notice how this bar and this bar are now different. This bar points to f3, while this bar points to f1. Now this is actually a case where this actually worked. Now the code, I didn't represent it explicitly, but the code for both bars is exactly the same. It's the exact same code. Right? It's exactly the same code. Yes, question?
If you, instead of having x equals 1,000, you have like z equals 1,000, and then instead of printing just x plus y, you had print x plus y plus z. So when it will go to like f1 go over c, and then if it doesn't find it, it'll go over.
Yeah, conceptually that's what happens. So if we actually do this completely, what will happen is it's a good question. Let me illustrate this. I'll illustrate it in like 1 second. Yeah, just hold that thought. So they're conceptually the same code object, but they have two different enclosing environment pointers. So now what happens is when we actually execute, we return bar. Now b2, oops. So now we have two dead frames, one with x is 10, one x is 20. Now b1 is a bar, b2 is a bar. They're the same bar, but they have different pointers. Now when I call b2 1, look what happens here. We're in. Now when I call b2 of 1, this parent is f3 now. So when I say x plus y, y is 1, and which x are we going to use? The 20x, because we just crawl up, we're going to use this one. All right, and your question is, if we don't find it, or we have a z out here, we're going to use the global one. And the way that the crawling works, so just to verify it works, let's prints 21, right? 20 plus 1. So I can actually open up another display. It's called show environment pointers. This will illustrate a little bit, and let's do z. Let's do z. Let's just do one of them. We don't need both. There's just another display. So basically, everybody's environment pointer by default points to the global one, unless you're in a nested function, in which case your environment pointer points not to global one. So I'm gonna just keep stepping through this. So the foo one points to the global, and now when I call bar here, I've just called bar, right? Bar's parent is f1, so I actually explicitly kind of change up to f1. Foo was defined, it had an environment pointer also, but since we didn't nest it, the environment pointer points to the global. So in this way, this is a complete variable lookup chain. When I look up y, I find it right away, easy. When I look up x, I don't find it here. I go up, I find it here. Good, we're good. When I look up z, right, y we got from this thing, x we got from this thing. When I look up z, not here, go up the chain, not here, go up the chain, we found it. My life is good. Now, if we want to say w, we do the same thing, all right? Go here, we don't find it, go up, don't find it, go up, don't find it. And then we probably go in the built-ins, right? I think some of you enter the built-ins. Is it a built-in? No, it's not. And then we say, you know, name error, or whatever error it gives us. So it's all just a lookup process. Cool. So, you know, why all this point about closures? Now, the point about closures is that Python actually doesn't, seems like a really elegant solution with all the pointers and everything. Python actually shortcuts all of this and doesn't actually keep all of this information about closures. Python actually does the equivalent of what you're kind of suggesting of, it actually just saves, it kind of cheats. When you make a bar with f1, it actually just stuffs this x equals 10 into the function itself. How did you figure that out? Did you figure that out from before?
No, just I was thinking that if you have something that is kind of nested along, and then you have to keep all these things of the parents, and then it's kind of waste of.
Yeah, it's kind of a waste of space, right? Yeah, because all these things, you know, we don't care about bar, we don't care about return, but we just care about the x. So it actually just inlines all of this into itself. Now, the consequence of it inlining is that you can't actually modify x. So in Python 2 at least, you can't actually change this value. Because it's actually been inlined into here, if you change it, then other people who point to it don't see the change. So it's actually read-only. The enclosing values are read-only in Python 2. In Python 3, you can use a thing called non-local. So in Python 3, there's a non-local keyword you can use to actually modify it, but we don't have to worry about that. So Python's implementation of closure is actually cheap. It actually just stuffs it in. So let's actually see how it works under the hood. It doesn't do this full elegant implementation. Let's go here. Let's go to our console. And okay, so we're going to do Python import test. If you don't have the code, don't worry about it. I mean, you can just watch me for the next like 10 minutes or so. Import dis.dis test, which disassembles it. Okay, so there's a lot of stuff going on here. Whoa. Okay, there's a lot of craziness going on. Okay, this sort of works. So recall that foo is just a function. Foo is a function that actually makes a closure. It has a make closure opcode that makes the closure and stores it in bar and then returns the closure. And B1 and B2 are simply just functions that are the result of it being made. Notice how B1 and B2 have exactly the same code. It's that their internals are a little different. So let me pull up the code again because it might be confusing if we don't see the code. Py. So remember, this is the code that there is actually a the global x. There is there's a nested function here. I'm gonna just move these a little bit. You can all see it. Oh. Yeah, Windows snaps to place, unfortunately. Okay. Now, thing's a little bit too small, but essentially B1 and B2 are just these bar functions. And there's some, it loads X, loads Y, and does this stuff. There's a special opcode. See, this load dref is a special opcode for loading from a non-local scope, because X is not a local, because X actually, it knows that there's no local named X, so it says look into the enclosing one for the X. So then it loads Y, which is X plus Y, binary adds them, prints, and just prints them and then returns none. So it's just the code for print X plus Y. So actually, let's look at what B1 is. Actually, that's let's inspect B1 and B2. So B1 is so everything is in test. So we have to say test.b1, test.b2 because we imported test. So the file is called test. So everything we access here must be saying test dot something. It's just a Python quirk. So if I say test.b1 equals test.b2, what would this return?
True.
It's false because they have different environment pointers, right? Because remember, B1 and B2 is the same code, but they're actually not equal because B1 has 10 stored in it, B2 has 20 stored in it, right? But what is true is test.b1
That's the code.
func code. Whoops. All right. Test.b2 func code. They're actually the same object, right?
Yeah.
At the same address.
Yeah.
So if I say test b1 func code equals test b2 func code, it's true. And it's even stronger. You can say is now. If you really care. Because they're actually the same piece of code. So again, b1 and b2 are not equal. b1 and b2 are not equal, but their codes are equal. So obviously something is different. So the closure is different. So B1 has a func closure. B2 has a func closure. And func closure is this inlining business that, let me make sure my notes on my phone, I don't have the notes on here, my lecture notes match up with this. Closure, input this. Func code, func closure 0. Okay, good. Okay, so func closure is some kind of a tuple. I guess there's only one thing in this tuple. In Python, it's hard to read, but this is a one-element tuple. A tuple is just a list of things. So if I say length.func b1 closure, it's 1. So if I grab the 0th element out of it, it's a cell object. It's some kind of cell. There's some special object. Or if I grab this test.b2 func closure, it's some cell object. So what is the cell object? So let's go into it. So dir again. We can get cell contents. Okay. I'm just guessing at the names, but let's see. I did this before. It's not a total guess, but usually that's how this goes. You just introspect and you just look at use dir. What do you think the B1 cell contents will be? Guesses? Taking bets on it.
It's like just a bunch of pointers.
Okay, well, if I told you the cell content is just a number, what kind of number would it be?
Just
So B1,
You want to be 10?
10. Okay, so we're guessing 10. Let's see. That's right. And what is the B2 cell contents? 20. All right, so that's exactly where it's stored. It's actually inside the function itself. We have a func closure thing that actually just jams the 10 or 20 in there. Whoops. So let's again, let me copy this code. Oh, we don't actually call it. But right, so whatever bar is, when we call bar, this is going to look super confusing. B11, B21. A lot of code. But when we call bar here, what do we? Yeah. So we actually look at the diagram and see where we are. This time when we call bar, x plus y, y is this one. Which one is x? What x do we use? F1, 10, because we use this arrow. Right, we use this arrow. And then when we call bar later, when we use this bar, oops, 21, right? So we'll back up here. This bar, it looks the exact same, but we're using this arrow for the 20. So the diagram makes it completely clear. Now, but what we just revealed is that in Python, there is no keeping this around. We actually just stuff x is 20 in here in a special cell. And we stuffed x is 10 in another one. We just stuffed it in. But we don't want to confuse it with a local variable, so it's called a special cell variable. So that's why when we access it with a bytecode, we actually don't use a load fast or whatever. We use a load deref or something like that. Like we look at the bytecode. This assembles it. It uses a load deref bytecode in X. So actually, let's see what this load deref does. Out of curiosity. So to see what it does, just look at the interpreter, right? Look at cval.c. So whenever you're curious about what anything does, Python C, and you all know how to go to load ref cell get. So I'm willing to bet you that is the that looks up the cell index and grabs the cell thing out, and that's it. Right? That's it. It's cell get. And let's look at free vars. What is free vars? Oops. So func closure is this thing. Now free vars is part of the code. Aha! Now what is this? This means that this code, this means that this code in B1, let's say B2 is the same thing. This means that X is a free variable, which means that somebody who defined it can assign a value to itself. So remember how the cell thing doesn't have a name, it just has a value of 10 or 20? It's matched up with this free vars thing in the code object. That's how we know X is 20. So in the code itself, remember how in the code itself we can't say what the value is because this code might be used by different functions. So this free vars thing is a way of communicating. So if we actually look at the documentation for include func object.h, this will solve the mystery of here. So remember how we had a func closure? Now it's a null or a tuple of cell objects. And now finally here's invariant. This is it right here. It says func closure contains the bindings for func code CO free vars. So the size of the func closure is the same as the free vars in code. So for every free variable in the code object, that one only had one, is called X. The func closure is actually the value of those things. So that's just how Python keeps track of these variable and values from nested scopes. There's a lot to. Yep.
How is it free?
Oh, it's called a free variable because it hasn't been bound by so the opposite of free is bound. So it's so in like programming language speak, if I just gave you a piece of code, let's not even stare at. Let's just look at this. If I gave you this piece of code, I'll ask you what variables are in this code. Just this piece of code. Just name me the variables. Okay, X and Y. There's two variables. Y is called a bound variable because it's actually bound to the argument here. When we call this function, we have to know what Y is because it's bound. X is called a free variable because we don't know where this X comes from. It could come from a global, it could come from something else. So that's just the notation they use. It just so happens here it comes from this thing. Yeah, it's just a name. It's just a naming convention. It's called a free variable. Questions? Okay, so, yep, so this is pretty much it for the function and code objects. I mean, there is, just going over the review, we actually covered quite a lot. So we covered code objects, which we covered before in class, the function objects, which again wrap around the code, and closures, which is the concept, the fact that function objects can be nested with them. There's not a closure object, right? There's not a separate closure object. It's just a concept for when you define a function inside another function.